All right, good morning, Physical Chemistry 2 class. Hope everybody's doing well. So, unfortunately, of course, we've got another snow day. So, I wanted to take advantage of, the ability to post the slides and, actually, it's kind of a nice opportunity to think about something warm today. So, the topic that we were going to do in class deals with actually one of the earliest historical developments in quantum mechanics, which was the understanding of thermal radiation, sometimes called blackbody radiation. And so this was actually a really key milestone, which we owe a lot to Max Planck. And of course, we've talked quite a bit about Planck's constant, H or H bar. And so actually, Planck discovered this constant through his analysis of thermal radiation. And so he arrived at an expression which we call the Planck blackbody law, which turns out to be actually really universal in describing the way that objects at non-zero temperatures, and if you remember from thermodynamics, everything is at a non-zero temperature, right? It's actually completely impossible thermodynamically to cool something to absolute zero. So basically, everything in this world has a finite temperature, and everything in this world, because it has a finite temperature, is constantly radiating energy away in a very particular way. And the underlying way in which it radiates energy away is understood through Planck's blackbody law. And before Planck's blackbody law, actually, there was a really astonishing prediction. People understood that objects at finite temperatures would radiate energy away, but there was a very incorrect prediction. Every physicist knew this was empirically incorrect, but they couldn't understand how to arrive at a correction. And that incorrect prediction was that basically, as the frequency of the radiation being emitted increases, the intensity of that radiation would actually increase without bound. And so this is known as the ultraviolet catastrophe, because basically, if you took the models that they were using and you asked, well, where does the radiation intensity start to diverge? It started to diverge for a lot of objects at ordinary temperatures around the ultraviolet. So there's a lot of consequences to that, but one consequence would be that if this were really the case, and the model that people used is called Rayleigh-Jeans law. If Rayleigh-Jeans law were really accurate, basically there would be no us. Everything would be fried to a crisp instantly, because everything would basically be emitting infinite intensity radiation at very high energies. And so here's a nice background slide. I don't know if you guys remember this movie, but this is from Terminator 2. Judgment Day. And so this is like basically when the robots, annihilate the world by launching a nuclear attack or initiating a series of nuclear attacks. So anyway, well, we're going to talk about Planck's blackbody law and a little bit about Rayleigh-Jeans law and compare and contrast the two, and talk about why it's useful. So actually, I want to make the case before we even get started that it is useful. And this is actually something that I think about quite a bit in my own research. And so actually some of you already know this because you work in my lab and you've thought about some of these problems too. But actually thermal emission and thermal radiation is an extremely important piece of our energy problem, of our energy economy and our energy challenge. And so just to give you a little bit of context, okay, so in this left figure over here, this is an image of the solar spectrum, right? This is the intensity of light uh, per color or per wavelength of light that falls upon our Earth from the sun. And so actually what you'll find is that there is a black curve right here, which turns out to be nothing more than evaluating Planck's blackbody law at a temperature of 550 Kelvin. And we'll talk about where that temperature enters into the expression later. But nevertheless, Planck's blackbody law depends on temperature and wavelength, or temperature and frequency, depending on how you like to use your units. And it just gives you a curve. And so this is the blackbody curve. And then this is the actual measured intensity of light coming from the sun. So you can see actually the blackbody curve is an extremely good model for the intensity of light coming off the sun. And that's because basically the predominant mechanism of thermal radiation of light coming from the sun is going to be, basically thermal emission from the surface. There's a whole bunch of chemical reactions and nuclear chemistry going on in the sun, but the net result is that you've got the sun's surface, which is heated to a fairly high temperature of 5,500 Kelvin, and then that hot body loses a lot of energy as thermal radiation. Okay, and so one of the things that I think is useful to think about is the fact that, well, if we break the sun's radiation up into these little chunks, and we call, okay, well, we've got 250 nanometers or so up to 400 nanometers. We've got some intensity, and we call that ultraviolet light, right? This is the stuff that we try to block with sunscreen to keep us from getting sunburned. We've got this region between 400 and 800 nanometers. That's what our eyes can actually see. And then we've got this region from about 800 nanometers onward, which is called IR. We can't see it, but our bodies sense it as heat. Well, actually, a good amount of the power that comes from the sun falls into this IR region. About 40% of the total power, in fact, reaching our Earth is IR. And so what that predominantly does is heats up the Earth. And importantly, most of the solar cells that we use to try to convert the sun's power into electricity are incapable of converting the IR energy into electricity, because simply put, the IR photons don't have enough energy to work with traditional solar cells. Okay, so that's an important figure to keep in mind. About 40% of solar power coming from our Earth, we basically cannot convert into electricity in a traditional way with a solar cell. And we would like to be able to do something with that, right? That's almost half the power that we're missing. And then another thing is, okay, if you think about all of the ways that we produce energy as a society, and this is, in our power plants, running our cars, doing things like that, heating our houses. So we produce, some net amount of energy per year, and 60% of that energy is wasted as heat. Okay, so basically the point I'm trying to make here is that if you can control thermal energy, and specifically thermal radiation, you can actually start to make a big impact for doing a lot better with creating energy, doing it much more efficiently, which of course is greener. So this is actually one way of harnessing thermal energy, and it's called solar thermophotovoltaics. And the idea is fairly straightforward in a way, although how you do it is actually very challenging. But the idea is fairly straightforward. So the idea is basically, okay, well, I've got this sun spectrum, right? This is what actually hits the Earth. And as I mentioned before, the sun spectrum is not really well engineered for solar energy conversion. It's very broad. It contains a lot of components, a lot of spectral power that actually are not usable by traditional photovoltaics. But a really big problem is how broad it is, right? If you look at it in an energy axis instead of a wavelength axis, what you can see is that you've got energy components that are all the way down, and this would be the IR, less than 1 electron volt. This is a unit of energy, which is relatively small, but makes a lot of sense if you're thinking about a semiconductor. All the way up to 4 electron volts. And so over here on 4 electron volts, this is really the UV region. And then this region between 1.5 and 3 electron volts, this is our visible region. So it turns out that there are a class of photovoltaics that actually work really well in this low energy region. So there's actually a very important class of PV cells that work around the 1/2 to 0.75 electron volt region. So really in the IR. And that's that region where we have a lot of power density, where our typical solar cells, like silicon solar cells, don't do anything. So there's an idea out there which is like, well, look, let me just use this broad spectrum of incoming solar energy to heat something up. And then what I'll do is I'll make that object have a very peculiar way of losing its energy as heat. And in fact, it will have a thermal radiation spectrum which is going to be well suited for my PV cell that has a really small band gap. Okay, and so how do you analyze how good these structures are? Well, basically, it all depends on knowing Planck's blackbody law, and then one other thing, which is what we call the emissivity. And the emissivity is something that is basically the same as an absorption spectrum. So everybody that's ever taken a UV-Vis absorption spectrum, which is everybody in the class, I know that for a fact, has dealt with unknowingly an emissivity function. And so basically, well, if you want to know how something is going to lose energy as thermal radiation, you basically need to know its absorption spectrum, or equivalently its emissivity spectrum, and you need to know the Planck blackbody distribution at whatever temperature the body is. So if I know this absorption spectrum, then I basically know how the object loses energy as thermal radiation, because the Planck's blackbody spectrum is just a formula that I can always evaluate as long as I know the temperature. So here I'm going to be talking about the temperature of the body that I'm interested in. So, you know, I could take the human body, for example, and if I knew basically the absorption spectrum of the human body, and I know the temperature of the human body, it's somewhere around 300 Kelvin, then I can evaluate Planck's blackbody law, and I can basically tell you the thermal radiation spectrum of your body, what it will look like. And I can do that for any other object. And importantly, I can think about trying to design objects that have a very peculiar emissivity spectrum such that I can do this kind of reshaping. And that turns out to be a really powerful idea. And why is it a powerful idea? Well, the photovoltaics, right, the solar cell that you're trying to work with, it has its own absorption spectrum in a way. This is called the response function of the photovoltaic, right? So this basically tells you, like, well, if I shine light onto the solar cell, does it produce electricity? And if so, how much? How efficiently does it take those photons and turn them into electrical current? And you can see this is the green curve. The green curve is actually the response function for a solar cell. And you can see that beyond a certain cutoff wavelength, which is called the band gap, it has no response, right? There is a certain minimum energy which is required to actually cause the solar cell to create electricity, and that's called the band gap. And if I have less energy than that band gap, meaning my wavelengths of my photons are longer than that band gap wavelength, then I will have no response. And then with energies above the band gap, right, I have some characteristic response. It's not perfect for all wavelengths, right? There's an actual response, which changes as a function of wavelength. So really what you would want to do is you'd want to have whatever shining on your solar cell match the response function of the solar cell itself. And that's the idea behind this solar thermophotovoltaics, is actually to create objects whose thermal emission spectrum are well matched to the response function of a photovoltaic. And actually, this has applications in light bulbs too. So I always like to think about light bulbs since we're in New Jersey. And hopefully you all have a lot of pride in light bulbs too, because they were invented here by Thomas Edison. So so here's a problem with light bulbs, right? And maybe you haven't thought of this, maybe you have, but if you grew up with standard incandescent bulbs, there's certainly one thing you know about them, which is that they get extremely hot. I mean, if you've ever had to change a light bulb, because the filament broke, okay, you need to wait like a long time so the thing can cool down before you can touch it, and it's really, really hot to the touch. So why is it so hot to the touch? It's hot to the touch because the light bulb works through thermal emission. Okay, so you heat this filament up. The filament is made of tungsten metal, which is, approximately a black body, meaning its emissivity or its absorption is basically 1 for all wavelengths. It's actually a little bit less than 1, but it is very flat, has like almost a constant value for all wavelengths. So the radiation coming off of the incandescent bulb basically looks very similar to a black body curve. So you heat this filament up, and you heat it up to like 3,000 Kelvin. And then the radiation comes off of the filament, And if you look at Planck's blackbody curve, with a temperature of 3000 Kelvin, what you find out is, yeah, you get a lot of visible radiation. So you get a lot of greens and blues and reds and yellows and oranges, but you also get a ton of IR radiation. And so your eyes don't see the IR radiation, but what does the IR radiation do to the bulb? It gets it really, really hot. So what that means is that, okay, you heat this filament up and it loses radiation. Your eyes can see a small fraction of that radiation, but the rest of it is wasted. So what do you want to do? You actually want to try to create a filament which is incapable of radiating infrared, right? Its emissivity goes to 0 for all infrared wavelengths, but its emissivity is high for visible wavelengths. So then basically what thermal emission prediction would be is that its blackbody curve times the emissivity, and the emissivity goes to 0 at infrared wavelengths, meaning there is no infrared emission. So this is another thing that can be done, right? And if you understand Planck's blackbody law and emissivity, then you can do it. And then why would that be important? Well, you end up with a light bulb which takes far less power to work. It's far more efficient. It has a longer lifetime, and it's made of some nice material like tungsten, as opposed to something like these fluorescent bulbs that have mercury in them, or these LED bulbs which have like cadmium or other toxic heavy metals in them. And these are also quite expensive. If you can do this with tungsten, this is, everybody knows a tungsten bulb is basically the cheapest thing, right? This is it's 37 cents per bulb. That's the cost to make this stupid thing. What's the cost of this stupid LED bulb? $45, right? It's ridiculous. So anyway, so there's a couple of things that are really interesting that you can do if you understand Planck's blackbody law. But let's actually get into the history, and let's get into a little bit of the details. Okay, so here are the main points of quantum mechanics that we kind of know so far. Okay, and you all know this first one now, hopefully very well from the midterm, one of those true-false questions. So there's special things about energy that we know from quantum mechanics. It's not that systems always have to have a precise, well-defined energy. That's not the issue, right? But the issue is that when you exchange energy or when you measure energy, you find that your measurement of energy or your exchange in energy is quantized, right? You can exchange or measure energy values that have discrete, well-defined amounts, right? Energy measurement and energy exchange is quantized. Now, please do not confuse that with the notion that you have to be in a state of well-defined energy at all times, right? We said that generically, quantum mechanical systems are not in energy eigenstates, right? They do not necessarily have well-defined energy. But when you do something like you measure the energy of a system, or you exchange energy with a system, meaning you absorb a photon, emit a photon, or something like that, then what you find is that then that happens in a quantized or discrete way. Okay, the certainty with which you know some things will happen impact the certainty with which you know other things. This is the uncertainty principle. We've got particles that show wave-like behavior and waves that show particle-like behavior. So this is something we've seen with the wave packet. The maximum amount of information you can know about something is contained in the wave function, right? This is how we specify our systems in quantum mechanics, through the wave function. And then we have, we've talked about some special wave functions like the energy eigenfunctions. But really there is not too much that you can say about the wave function other than, it needs to be smooth, its derivative needs to be smooth, it needs to be single valued, it needs to be normalizable, that sort of thing. Okay, so what's special about Planck is that, it was really his advance that led to this realize that energy is exchanged or measured in discrete and quantized amounts. That not all possible values of energy are possible to exchange, and not all possible values of energy are possible to measure about a system. Okay, so I think we've seen this timeline maybe once before at the very beginning, but it's important to kind of think about where this all fits in. So Planck comes in really at the very dawn of quantum mechanics. And this is, I mean, it's really pre-quantum mechanics at this time because we don't have this notion of a wave function yet. We don't have this notion of a Schrodinger equation yet. We don't have the postulates. So Planck comes in around 1901 and solves this issue of what we call the ultraviolet catastrophe, right? This prediction that when objects lose radiation, lose energy as radiation, that they will do so in an unbounded way as energy increases. Okay, so slightly after Planck, we've got Hertz discovering the photoelectric effect and Einstein explaining it. About a decade after Hertz and Einstein, we've got Niels Bohr, who's writing down a very simple quantized model of the atom. About 5 years later, we've got the famous Stern and Gerlach experiment, which we've talked quite a bit about. And then 4 years later, we've got Schrodinger, who actually starts to write down the laws of quantum mechanics. Okay, so we're really at the beginning with Max Planck. So at this time, in the 1900s, this was known. Okay, these following things were known: that all materials with a finite temperature emit radiation, that the intensity and energy of the radiation they emit will increase with temperature. Okay, so that means, you know, if I've got a cold oven, right, it's going to be emitting radiation, but the energy of the radiation that it emits and the amount of radiation it emits will be lower than if I have this hot oven down here, right? So I've got this nice hot pizza oven, and you're sitting in the restaurant with the pizza oven, you're all feeling, you know, the nice warm glow of this oven. Well, if the oven has no fire, it's still glowing, right? It's still at a finite temperature, but the intensity of that glowing that the oven is doing is much, much lower because it's much, much colder. Okay, so at the time before Planck, the classical way of thinking led people to believe that the intensity of higher energy radiation will tend to infinity at finite temperatures, and this was called the ultraviolet catastrophe. And so Max Planck had this revolutionary idea, which is that he would quantize the energy that was emitted from objects, and this actually alone, this one change, made all the difference, allowed him to derive a formula that did not diverge at finite temperatures. So before, basically, people thought that, well, I've got these things, right? They can emit energy. They're probably doing so because their constituent parts are moving, and they can move with any energy possible, and then they can accept or release any energy possible. And Max Planck said, nope, that's not the case. The constituents of matter can only accept or release energy of certain quantized values. And in particular, they will be integer value, or they will be proportional to integers times some constant. And then because he actually had data, and this assumption allowed him to derive a model, he was able to fit his model to the data and extract a number which he called Planck, which was later known as Planck's constant. I don't think he called it that. So it's important to realize that the whole reason that people knew all of this stuff was true is because you had this person named Gustav Kirchhoff, and Gustav Kirchhoff has many advances associated with him, including something called Kirchhoff's law, which you might know if you've ever studied circuits. Anyway, he had created a device which is basically a camera. I mean, not a camera as in like with a lens, but your web camera. Photons hit the web camera, and the web camera registers some signal when photons hit it. And so he had created such a device that allowed people to measure radiation intensity as a function of wavelength and frequency. So this device is a component of any spectrometer you've ever used, right? Just some fancy version of what Gustav Kirchhoff created in the 1880s. So this allowed people to do things like, well, take a piece of glowing iron and measure the radiation coming off of it, or take a glowing brick and measure the radiation coming off of it, and stuff like that. Okay, so then with this object, you can create these spectra. Right, these are just crude little sketches of radiation intensity as a function of wavelength for different temperatures. And so just think for yourself for a minute which of these spectra should correspond to the lowest temperature and which should correspond to the highest temperature. Okay. And so I don't think I need to really go through this quick review of electromagnetic waves, but I'll just, here's the different regions of the electromagnetic spectrum, and here's what I want to concentrate on is that if you actually take now the Blackbody law, which wasn't known until Max Planck wrote it down, and evaluate it for different temperatures, here's one of the features that you find. So at low temperatures, right, the intensity of radiation, the total power density coming off the object is lower, right? So that means the peak of the curve, it hits at a lower value, and the total area under the curve is smaller. But here's another thing. The peak of the curve tends towards smaller energies or larger wavelengths at lower temperatures. So as we evaluate Planck's Blackbody law for progressively higher temperatures, and this bottom curve is 3,000 Kelvin, this is 4,000 Kelvin, 5,000 Kelvin, and 6,000 Kelvin, what we see is that the position of the peak blue shifts, right? It goes to shorter and shorter wavelengths, which means larger and larger energies. So the peak of the Blackbody curve at 6,000 Kelvin is about 483 nanometers, right? That's blue light, basically. And the peak of the Blackbody curve at 3,000 Kelvin is 724 nanometers. Basically, that's red light, almost IR. And so this is the temperature of a light bulb, by the way, 3,000 Kelvin. And this is the temperature of the sun. Okay, so you can see for yourself that the intensity of visible light, the relative intensity of visible light coming off from the sun is much, much greater than the relative intensity of visible light coming off from a light bulb at 3,000 Kelvin, just because of the temperature. Okay. So, so here was the idea that people were using at the time. So they had this notion that, well, I can have this sort of like vibrational type motion, what we call normal modes of my object. Any solid is going to have these normal modes, right? You can think of it if you want to think of so people at that time were probably thinking about continuous solids, and so their picture was very much like that of, taking like the head of a drum, if you've ever played a drum, or stretching some kind of fabric tight and asking like, well, how can I displace the fabric, right? Now we think more in terms of atoms, and so this would be like the collective motion of a bunch of atoms in a solid. But however you think about it, you can actually count the number of such modes as a function of frequency, and basically the number of possible modes is going to increase with frequency, because higher frequency means shorter wavelength, which means more possible ways of fitting that motion into a finite region of space. And so the key idea was that each one of these modes can absorb and emit radiation. And how many modes are there as a function of the frequency of the modes? This is the expression right here. Okay. And so what they did then is they said, well, and also each one of these modes is going to have an energy associated with it. And so we'll equate the energy of that mode to Planck's constant, Boltzmann's constant times temperature. Okay, and so now this is what was called Rayleigh-Jeans law. All right, so the energy per mode times the total number of modes is going to give you this quantity called Rayleigh-Jeans law. And so here's the question where I ask you, or here's the time when I ask you, well, what is this actually quantifying? What are the dimensions of this Rayleigh-Jeans law? So it's a good time to press pause on this video and think about this for a minute. Okay, so now that you're back, let's go through it. So this this is our frequency, right? So our expression overall is 8 times pi times nu squared times Boltzmann's constant times temperature divided by speed of light squared, all times differential in frequency. Right, so let's go through all the dimensional quantities one by one. Nu squared, frequency squared, of course frequency is 1 over time, so frequency squared is 1 over time squared. kBT, so remember Boltzmann's constant is energy times temperature, or sorry, energy per temperature, and T is obviously temperature. So overall, I've got energy comes from kBT. Energy over temperature times temperature is going to give me just energy. I've got 1 over c squared, and of course c is the speed of light, so that's in meters per second. So 1 over c squared is going to be dimensions of time squared on top, and divided by dimensions of length squared on bottom. And finally, I have my little differential element of frequency, which is going to also have dimensions of 1 over time. So I combine all of these things together. Oh gosh, I'm getting cut off at the bottom. Very sorry about this. So I've got 1 over time squared times E times time squared over length squared times 1 over time. So when I cancel all my dimensions, at the end of the day, I'm going to have energy over time times length squared. Energy over time is a power, and 1 over length squared is length squared is an area. So what we do is we call this a power density, right? This is a power per unit area emitted from my object. And so here's the thing. This is the power per unit area emitted by my object at some temperature, but how does it change with frequency? So if I make V larger and larger, right, this thing is going to increase as the square of V. So you can even go into Wolfram alpha if you want and plot this if you don't see it right away, but this is basically going to diverge at large V for any finite temperature, right? As long as T is non-zero, this thing actually tends to infinity at larger V. And that was the source of the ultraviolet catastrophe, right? The density of these modes was thought to grow quadratically with frequency, and that clearly seems to be wrong, right? So this is, our world where the Rayleigh-Jeans law is correct. Clearly not really our world. Okay, so here comes Max Planck. And so he proposes that each mode is not capable of absorbing just any old energy value. It can only absorb energy in discrete units. And then he further said that, well, if I'm going to say that I'm going to absorb or emit energy in discrete units, I might as well state that mathematically by saying the energy that can be absorbed or emitted is proportional to an integer n times some constant times the frequency. So what he did basically is he proposed a proportionality between frequency and energy. And now that proportionality constant bears his name, and it's known as Planck's constant. Oh, I don't think I said this, but in the eventuality of time, in case I forget to say it later, Max Planck was recognized with a Nobel Prize for this development. So that was about 18 years after he wrote this whole stuff down. So what are the dimensions of Planck's constant then, right? If we should know this by now. So its frequency is 1 over time, right? N has no dimensions, it's just an integer. So then Planck's constant times 1 over time must give me energy. So then Planck's constant must have dimensions of energy times time. Okay, so here's the idea. Each mode can only absorb energy in discrete units proportional to the frequency of the mode. The proportionality constant is some integer times Planck's constant. And with this assumption, he was able to write down the average energy per mode in this following way. Right, so up top I have h nu again, so this is an energy. Down here I have h nu, which is an energy, over kBt, which is an energy. So the argument to this exponential has no dimensions. 1 has no dimensions. So this average energy per mode has dimensions of energy. And if you want, I have some notes at the end for how you can actually arrive at this final expression. But the phenomenology of this whole thing is a lot more important, so you can keep that in mind. All right. So, simply put, what he did is he stuck these two things together, the way of counting the modes times the average energy per mode in his new prescription, and what that led to was Planck's blackbody law. Okay, and so now there's a difference here, and actually I've made a mistake in my c. This should be c squared, but anyway, everything else is okay. So now instead of this kBt times nu squared, he's replaced it with h, Planck's constant, times nu times nu squared. So h nu is energy, and nu squared is counting the modes. Right, and this is our expression. This is left over from our average energy per mode, right? H nu dV over this exponential was our average energy per mode, and then 8 pi nu squared over c squared was our number of modes per frequency. So this is called the Planck's blackbody law. And if you evaluate it at a particular temperature, it looks like this curve right here, right? This one that is bounded. So we still have a sharp rise in the beginning from this nu to the third term, but as frequency becomes very large, this exponential over here starts to take over. So you're dividing by a number which is growing exponentially with nu. And so if you're dividing by an exponentially large increasing number, of course, you're going to become exponentially smaller. So this matches extremely well, how things actually behave in the real world, unlike the Rayleigh-Jeans law. So you can see actually there is a little bit of agreement between Rayleigh-Jeans law and Planck's blackbody curve for low frequencies. It's just at some critical frequency, like they start to depart from each other. Okay, so you know it's coming. I'm going to ask you to do the dimensional analysis for Planck's blackbody law again. And when you do it, I think you're going to want to fix the factor of c. Anyway, go ahead and press pause. You can do it with c cubed or c squared. It's a slight difference, which we can talk about if you have. They're both not, it's not that one is incorrect and one is correct. It's just that one is going to give you one kind of density and one is going to give you a different kind of density, and we can talk about the difference. Okay, so notice now that all of a sudden I fixed my c, and so let's do the dimensions again. So Planck's constant up top is energy times time, as we said before. Nu to the third is 1 over time cubed. 1 over c squared is time squared over length squared. And dv is 1 over t, right? And this whole thing down in the denominator of the second piece, that has no dimensions. So we put this all together, right? E times t times 1 over t cubed times t squared over L squared times 1 over t. In the end, I get, again, E over time over L squared. So this is, again, a power density. And so if you went through the analysis with c to the third, basically you would end up with 1 energy over length cubed. And so instead of being a power per unit area, you would be an energy per unit volume. So that's the difference. Okay. So really quickly, though, I just want to show you visually. So that's basically Planck's blackbody law. We've seen it. You've seen the curves before. I also find it a little bit helpful to see, what these normal modes look like in an atomic sense. And so remember, when we're talking about these objects, right, we're basically talking about, big macroscopic solids, things that have like many, many atoms. And so we've talked about the vibrational motion of just a diatomic, right, and we know that it can stretch. And we've talked about even the vibrational motion of triatomics and stuff like that before, maybe in Phys Chem 1, maybe you've seen it in analytical, and so on. But you don't often think about the vibrational motion of like a macroscopic solid. So there are all of these different unique ways to displace the atoms in a solid. And so each unique way is called a normal mode. And this is actually an illustration of one particular normal mode. So it's actually very interesting to realize that these normal modes can actually be delocalized over the entire solid, right? They're involving the motion of the entire solid. This would be actually a fairly low energy normal mode. The low energy normal modes will tend to be very delocalized. On the other hand, the high energy normal modes will tend to be much more localized, so they may only involve small regions of the solid. And that's very much an analogy to small molecules, right? The fingerprint region of, not the fingerprint region, but the, when you take an IR spectrum and you talk about the functional group signatures, right? Those are fairly high energy, localized normal modes of the molecule. So same thing applies with a solid. So anyway, each mode has some characteristic frequency nu, and the mode can absorb or emit radiation with integer multiples of this frequency. So this whole thing that we're watching is characterized by one single frequency nu, right? This whole mode has some characteristic frequency. And if we want to excite this mode into higher energy states, we need to give it integer values of the energy h nu, right? And so what happens when I excite it to a higher energy state? Well, basically the amplitude of motion of this mode increases. So, you know, I'm still going to wiggle all of the atoms in this worm-like fashion in the same pattern, but the actual magnitude of displacement along this wiggle pattern is going to increase as I go to higher energy states of this particular mode. And so another just interesting feature, this is kind of, you know, echoes what we've been saying about the energy eigenfunctions, is that, okay, so you have some total number of normal modes of your crystal, just depends on how many atoms you have. In particular, it's on the order of 3 times the number of atoms in your crystal minus 6. Okay, so if you had 1,000 atoms in your crystal, then you've got about 3,000 normal modes minus 6. So whatever that number is, you do the arithmetic yourself. Okay, so what's important about those normal modes? Each of them is a unique way of displacing the atoms. And what it means is that any way that you can distort the crystal, you know, anything you could imagine doing to it mechanically, you know, taking your atomic force microscope tip and driving it into the crystal and doing something dramatic to it, any motion of the crystal atoms can be written as a superposition of the different normal modes of the crystal. So then another way of saying that is, well, in general, the crystal is not in any one normal mode, right? It is not in some well-defined vibrational eigenstate, but its motion can always be described by some combination of the normal modes. Okay, and so one of Planck's key insights is that not all of these modes are active at finite temperatures. At low temperatures, only low-frequency modes will tend to be active. And so that realization, that sort of inherent idea that underlied his expression, is what allowed the Blackbody, the ultraviolet catastrophe to be resolved. And so in fact, you can actually, if you know the temperature of your crystal, you can actually compute the probability that you're occupying some normal mode with energy n. And so basically this is E sub n is nothing more than Planck's constant times the frequency of the mode times some integer n. And basically the integer n can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each normal mode has actually excited states, and so that's kind of a funky idea, because it's sort of like, instead of just one energy eigenstate, you've got a whole manifold of energy eigenstates for each unique way of displacing the atoms. But if you can get your head around that idea, it's very similar to what we've been talking about with, for example, the particle in a box energy eigenfunctions. Okay, so that's it. If you are very interested in deriving Planck's Blackbody law, there's some notes to help you do so. All of these notes, by the way, are up on Blackboard under Blackbody radiation updated slides. So, all right, that's going to do it for Planck's Blackbody law, and I'll see you Monday for class. You can ask me any questions about the slide then, and of course, send me any emails if you have questions.